Okay, here we're going to do section 9.9 problem 7 from the textbook. And this is an important example problem. It's just an example, but this type of problem is important. It deals with conservative vector fields and the results of having a conservative vector field. But the reason this is important is there will be a question like this on the midterm and probably on the final. Not this exact question, but a problem just like this, where it says something to the effect, the three elements that are at play as, I've got a vector field, I want to know if it's conservative, we have to show that. Then what we do is we have an integral of that vector field, and we're going to evaluate it two different ways. They have to give the same answer. So once we show it's conservative, then the question is, well, find that integral two ways. Find a potential function for the vector field, and then evaluate the potential function at the endpoints, take the difference, that's equal to the integral, or evaluate the path integral using any convenient path between those 2 points. Once you know a vector field is conservative, you know those three things are equivalent. Okay? Well, there's two things. Find the potential and the difference in potential at the endpoints gives you an answer. Doing the integral along any path you like gives you an answer, and those answers must be the same. So the reason I like this as an exam question is it tests many things. The reason you like this as an exam question is you know if you're right. Because in the exam, you do it one way, you do it the other way, they got to be the same. And if they're not the same, you know you've done something wrong, and that gives you a hint to try to find the problem. Okay. So this is an example problem statement. We haven't seen this. We're actually given a very specific point in space here. We want to do this. We got some crazy vector field here dotted onto dr. Okay. So the idea here, if I'm going to test to see if it's conservative first, the thing is says show this is independent of path. That just means you're supposed to know that means, oh, I'm supposed to check if the curl of this thing is 0. That's what you're supposed to know, because that's the same as being independent of path. So I've got a vector field here, okay? That's 2y squared x minus 3i plus 2y x squared plus 4j. And now the question of is that integral independent of path is the same as asking is the curl of f 0. Okay, di x, di y, di z, and then I have 2y squared x minus 3, then I have 2y x squared plus 4, and 0. Okay, so the question is, what's the value of that determinant? And we expect it to be 0, otherwise this problem doesn't make any sense. Okay, so this becomes 0i, 0, 0, minus 0j, di by dx of 0, 0, di by the z of this function xy is 0, plus k. Okay, and now for k I have di by dx of this. So that's 4xy. Okay, then I take minus di by dy of this, which is di by dy of this is 4yx. The constants go away, and yeah, this thing is 0. Okay, 4xy minus 4xy is 0. So to every component of the curl is 0, therefore the curl is equal to the 0 vector. And yes, we have f as a conservative field. So now we've shown that this thing must be independent of path. Okay. So now what we have to do is find a potential function. This is probably the most work of these type of problems. It can be easy or it can not be easy. Okay. Okay, so I'm going to erase this here because we sort of see this now. I'll remind us, we'll draw this again. But for now, okay, we have to find a function phi. So we need that f equals the gradient of phi. So let's write this out to see what it really means. This means that di phi di x I plus di phi di y j equals that. That means that we have some function phi such that the partial derivative of phi with respect to x equals 2y squared x minus 3. And at the same time, the partial of phi with respect to y must be the y term there, 2 y x squared plus 4. So we have simultaneous first order partial differential equations. So we start with one, integrate it out, and then apply that result to the second one to obtain a final result. Okay? So the first thing we know, if we take this guy here, okay, is that, okay, well, phi of x and y equal to the antiderivative 2y squared x minus 3 dx. Okay? So the y's are constant here, so this becomes 2y squared, and integrate, so that becomes x squared over 2, right, minus 3x. Okay? And then this. This is the single most important part, I would say, or the single easiest part to make the mistake on when you're trying to calculate this or solve for this potential function, is when you do the antiderivative with respect to x, or integrate out x, you consider y a constant, so this just becomes, okay, 2y squared, x squared over 2, yep, minus 3x, yep. And then normally we know we have a constant, right? The antiderivative is unique to within a constant. Now, because we're just integrating with respect to x, this constant can, and in general is, a function of y. So you write it as g sub y, or any function as a function of y. And we're going to solve for this function when we go back into this equation here, okay? So that's critical. This thing is critical. You don't forget that. Okay, let's just simplify this for a second. So this is x squared, y squared, okay, minus 3x plus gy. We know that phi x and y equals this. We just don't know what g of y is yet. That's where the second differential equation comes in. Okay, so I know this. So let's take the y derivative of this thing. Die by y of what I've got so far, x squared y squared minus 3x plus gy. And let's just evaluate that for a second. So that becomes 2x squared y, that's 0, plus g prime y. Okay, and this thing must equal, that whole thing must equal this. 2x squared y plus 4. Okay, so this first part came from the solution I got from the x partial derivative, including this unknown function. I took its derivative with respect to y and set that equal to this. So now I've used the second equation. And so now I could solve for gy. And this is actually easy. This and this cancel. So this tells me that g prime y equals 4, which means that g of y equals 4y plus another constant. Okay. That constant we're not going to worry about because it's going to be subtracted away when we do the difference in the potential between the two endpoints. Okay. So this means then that our potential function is x squared y squared minus 3x plus 4y plus a constant. Seeing how to find the potential function given the original vector function is very important. Sometimes it's pretty easy, sometimes it's less easy, but it's important all the time, and you have to do that. Okay. So that means, so we have this thing now. So then if we go back to our original problem, we were asked, well, let's go 3 to 6, 1 to 2 of f dot dr. Well, this thing just equals phi at 3, 6 minus phi at 1, 2. So now it's really easy. We just plug in the endpoint and minus the original point into the scalar function and see what we get. So this thing equals, okay, so we've got 3 squared, we've got 6 squared minus 3 times x, which is 3 times 3, plus 4 times y, which is 3 times 6, minus, okay, and then we put 1 and 2 in there, so we get 1 squared, 2 squared, minus 3 times 1, plus 4 times 2, right? And this thing equals 330. I'm assuming that we can handle the math between there and there. Okay? But you see the thing. We have a vector function. We proved it's conservative. Then we go and search for the potential function. If it's easy to calculate, relatively easy, and this one was relatively easy to find, then this contour integral becomes very simple to evaluate, because now we just evaluate this potential at the end point of the integral minus the potential at the initial point of the integral, and we get our answer, right? Notice that, remember that these integrals are scalar results when we're done, okay? So the scalar function evaluated will give us a scalar, just a number, and that's what we should be having. So let's remember the number 330, because now we're going to finish this problem off the last way, which is find a convenient path between the 2 points. And let's do the contour integral and see if it's the same, or demonstrate, show, prove, whatever. Not prove, just demonstrate that in this case it is the same as the value we got for the potential function. So this is evaluating this thing in our 2 different ways. When you do this, you need to be sketching out the curve, okay? So our curve starts at x1, 2, so I'll go here, 1, comma 2. And then, let's see, x is 2, 3, okay? This is 3, comma 2. And then up here, at y equals 6, we have 3, comma 6. So this is point A, this is point B. You don't have to name them that, but that's what we have. And we're integrating our function between this point and this point. And we can go any path now. And there's 2 not crazy paths to go. One way is to do this in 2 steps. C1, C2. We're in this direction because I got to start here and end here. Or I can go straight from this point to this point. Okay. I'm going to solve the first one, C1 and T2. In the note mod, and these notes in handwritten form are already on the OWL site for you. Okay. Notice I could take any path. I could start here and go like this. I'd get the same answer. That would be insane, but I could do it. We're not going to do that. Okay. So let's do the C1 plus C2 case here. So let's look at C1. Okay. Along C1, we're varying x and keeping y constant, right? Y is constant at the value 2. X goes from 1 to 3. Okay? So along C1, I'll just say, well, x equals, and then what was y equal? Then what is dx equal? And what is dy equal? Because those are the things that I need. Because I'm going to do, by the way, remember, I'm going to do this integral. What do we have? This is what we're doing. Okay. To do that integral, right, we need to know x's and y's, dx's, dy's, and limits of integration. So now when I set this path up, C1, x, what is x as I vary between 1 and 3? Well, x is just equal to x. I'm going to let x go from 1 to 3. Okay. What's dx? Well, dx is just dx. What's y along this path? Y is not 0. Y is constant at 2. Y equals 2 along that path. What is the change in y along that path? 0. Okay. So that means when I convert this integral to 1 only from x, dy kills this entire term here, okay, because dy is 0. And then here I just put in the values I had for x and y and dx. So I've got x from 1 to 3, then I've got 2, what's y squared? 2 squared x minus 3 dx. That's my integral. So this is just as simple as it seems. 1 to 3, 8x minus 3 dx. Okay, this is, so yeah, we got 8x squared by 2 minus 3x. Okay, so this is 4x squared. So this is 4x squared minus 3x. 1, and this thing is equal to 26. That's the value of C1. Okay. So we'll remember 26 here, and now we just say, okay, well, what's the contour along C, the integral along C2? Oops, I shouldn't erase that part, but there we go. So I'm going to keep this 26 we had. I'm just going to assume here, the integral C1 equaled 26. Okay, we'll remember that. So now for C2. Okay, so along C2, well, what is x? What is dx? What is y? What is dy? Okay, well, y equals y for y between 6 and what, 2, right? Because y starts at 6 here and go up, up starts at 2, goes up to 6. Okay. What does x equal along this thing? Well, x is constant at 3. What is dx along this path, straight up and down? It's 0. And dy is just dy. So now, the first term in my integral shouldn't have erased that here a minute ago. 2y squared x minus 3 dx plus 2yx squared plus 4. You don't have to keep rewriting this, I just shouldn't have erased it. So now, when I do this along C2, this guy will be 0. Okay? This is why we like to do the 2 straight line paths, because 1/2 the integral dies each time you do it. Okay? So this thing becomes 2 to 6 of 2y. Okay? X squared is 3 squared, right? Plus 4 dy. Okay? 6, 2. Okay, no, we got 9, 18 y plus 4 dy. Okay. Okay, so this is 9y squared plus 4y, 6 and 2, so this becomes 9 times 36 plus 24 minus 9 times 4 minus 8. And this thing equals 304. Okay, that's what C2 is. So now look, this integral C, I wrote as C1 plus C2, which is 26 plus 304, which is 330, which is the same value we got, as we had to, the same value we got using the potential method. Okay? So if I'm doing this problem on the exam, this is it. I first showed that the curl of f was 0. That shows it's conservative. It shows the path integral is path independent. Then I found the scalar, the potential function. And then I evaluate the potential function of the 2 endpoints. I got a difference of 330 units of whatever it is. Then for the second part of the problem, I chose a path between this point and this point. And I like these straight line paths. It breaks into 2 integrals, but they're doable. And when I calculated them independently and added them up, we got 330, same as we had to do before. The last part of this problem, and this is done in the notes that are on the site and available to you, is, well, you can do a different one. Go straight from this point, this point. Now, I can eliminate x or y. I would probably write y as a function of x, slope and intercept. That give me y equals function of x. Then I would say, okay, I'm going to go from x from 1 to 3. And now dx would be dx, but dy would not be 0. It would be d by dy of whatever that line equation is, and I'd get some function of x there. And so I'd have a more complicated case. Both terms would live, but it'd all be a function of x. Then I integrate that, and I have to get the same answer. And that's done, like I say, in those notes explicitly. Okay. that problem encompasses a lot of things that we've done in this course so far, and that problem is a stereotypical example of a problem we would have on the midterm or the final.